In this video, we'll continue to work on drawing Lewis structures, now working on drawing Lewis structures of polyatomic ions. So let's look at something simple like the Lewis structure of the hydroxide ion. Okay? So, obviously the connectivity is easy, right? So we draw a connected structure, right? Then we look at our valence electrons, and it's in the valence electrons part that drawing Lewis structures of ions are different. So we know oxygen has 6 and hydrogen has 1. That would be 7. But because we have a negative charge, we have to add an electron for every negative charge. And conversely, if we have positive charges, we'll have to subtract electrons. Okay? So that means we've got 8 electrons to distribute, not 7. Well, we've already accounted for 2 of them because of the bond that's already drawn, leaving us with 6. 1, 2, 3, 4, 5, 6. Right? And so that is our distribution of electrons. Right? We're out of electrons now. Now, if we have an ionic species, then the whole species is going to carry the charge. But we also need to be able to look back at which atoms are carrying the charge, which takes us back to that question of formal charge, right? So if we do formal charge for hydrogen, right? Hydrogen, right? The formal charge for our hydrogen brought one electron. It gets to count half of the electrons in that bond. And so the formal charge on our hydrogen is 0. If we look at our oxygen, right, the formal charge on our oxygen brought 6, right? It has 6 electrons that it's not sharing with anything else, right? It gets to count half of the 2 electrons in its bond. It's 6 minus 7 is -1, right? So our formal negative charge is on that oxygen, right? We can assign a charge to an atom, right? And so that then is the best stable Lewis structure of the hydroxide ion, right? So with ions, we have to deal with changing the number of available valence electrons because of the charge, and then we also have to go back and consider the formal charge. Which atoms are carrying the charge in the species? Let's look at another common polyatomic ion, the NH4 plus ion, or the ammonium ion. Don't know why that messed up. Okay? So, if we draw the ammonium ion, obviously hydrogen can't be in the middle, so we have to put our nitrogen in the middle. Hydrogen's around it. Right? Nitrogen, right? If we do our valence electrons, right? Nitrogen brings 5. 4 hydrogens bring 4 times 1. That's going to equal 5. That's going to equal 4. That's 9. But we have a positive charge. So because to get a positive charge, we have to take away an electron, right, because of the positive charge, leaving us with only 8 electrons to distribute, right? We have 4 bonds, So we've already accounted for all 8. There are none left. That is the proper electron distribution. Now we have to look at formal charge, right? So let's focus on the nitrogen in the center, the formal charge on the nitrogen, right? Nitrogen brought 5. It has no unshared electrons, but it can count half of the 8 electrons around it. So that's going to be equal to 5 minus 4, leaves us with positive 1, which was the overall charge on the ion. And one thing we notice is that the sum, right, the sum of the formal charges is equal to the charge on the ion. Okay, so we've got our plus, and so that is the proper Lewis structure of the ammonium ion with the formal charge on the central nitrogen. Let's look at an unusual ion here, the CH3 minus ion, called the methanide ion. Okay, so hydrogen can't be in the center, so carbon has to be. So we put in our hydrogens around the outside. All right. We have to consider our valence electrons. All right, so carbon brings 4. Our 3 hydrogens bring 3 times 1. Right, so that's 4. That's 3. Gives us 7. But we have a negative charge. So we have to add 1 electron for the negative charge. Leaves us with 8. Because of the bonds, we've already accounted for 6 of those, leaving 2. The only atom that needs more electrons is the central carbon. Put 2 electrons on the central carbon. That uses up all of our available valence electrons. Now, right, the thing that looks odd to us is that carbon in the center with only 3 bonds. So let's focus on that. So the formal charge of our carbon brought 4 electrons. It has 2 that it's not sharing. It can count half of the 6 electrons around it in its bonds. That's 4 minus 2 plus 3 is 4 minus 5 equals negative 1. So the formal charge, the negative formal charge, is on the carbon. And there is the best Lewis structure, including the formal charge placement, for the methanide ion. Let's look at another unusual ion, an iodine difluoride cation. Okay? Now, right? So fluorine is more electronegative than iodine. So when we're drawing the Lewis structure, the iodine will go to the center with the fluorines attached to it. Right? If we do our valence electrons, right? Iodine normally brings 7. We've got 2 fluorines. That's going to be 2 times 7. So that's going to be 7. That's going to be 14. Leaves us with 21. We've got a positive charge. So since we have to manipulate electrons, we have to take away 1 electron to account for the positive charge. leaves us with 20 valence electrons. Because of bonding, we've already accounted for 4 of those, leaves us 16 to distribute. Start around the outside, distributing in pairs to give the outside atoms an octet. There's 6. There's 12, 13, 14, 15, 16. We have used up all 16 of our electrons, right? And we have no electrons left, right? If we consider our formal charges, right? Our formal charge of our iodine, right? Iodine brought 7. At this point, it has 4 that it's not sharing. It gets to count half of those 4 in its bonds. Right? And so the formal positive charge is on that central iodine. And there is the Lewis structure of that ion. Let's consider another potential unusual ion, the SF5 minus, sulfur 5 fluorines and a negative charge. Right? Again, fluorine being the most electronegative element, can't be in the center, so sulfur has to be. So we put our 5 fluorines around it. Right? Then if we look at our valence electrons, right? Sulfur brings 6. 5 fluorines is 5 times 7, right? That's 6. That's 35. Gives us 41. But remember, we have a negative charge. So to account for the negative charge, we have to add 1 more electron to account for our negative charge. Gives us 42 to distribute, right? Because of bonding, we've already accounted for 10 of those, leaving us 32 to distribute. And we start around our fluorines on the outside. Since they already have 2, we can add 6 around each one. 6 times 5 will be 30 electrons, right? That accounts for 30 of them, leaving 2, and so that gives us an unshared pair on the sulfur. Remember, since sulfur is in that 3rd period, it can have more than 8 electrons around it. Here it has 2, 4, 6, 8, 10, and the unshared pair makes 12. Right? Now we have to look for where the formal charge is. We should be noticing a pattern that in these, the formal charge often ends up on that central atom. So let's look at the sulfur first. So the formal charge on that sulfur brought 6 electrons, right? It's got 2 that it's not sharing. It gets to count half of the 10 in the bonds around it. So we have 6 minus 2 plus 5 equals 6 minus 7. And yes, the sulfur is carrying that negative charge. And there is the Lewis structure of that sulfur pentafluoride anion. So that gives us an indication of how to deal with ionic species.